Hello, everyone. It's the one and only Radio Craftinity with another episode of our podcast series, Machine Learning Made Known. As usual, I'm here with my co-host, Ola, and Andrew.
Yo!
Hey!
And of course, our marvelous guest. Today, we want to talk a little bit about object detection, and who would be better to do that than with Craftinity's co-founder and CTO, Mattew Opala.
Hello, everyone.
So why don't we start with the basics? Matthew, could you tell us what exactly object detection is and how it can be useful?
Sure. Object detection on still images is one of the most common tasks tackled by machine learning algorithms. The goal of object detection is to predict tight bounding boxes around objects and their classes. It may be a part of a larger system, such as a street-to-shop search engine, or it could be tuned to a specific case like face detection. That is a practically resolved problem at Facebook.
Could we also use it to complete a more complex task? For example, a super advanced robot or self-driving car?
Yeah, sure. If you remember that scene from Terminator, the movie, there was a cyborg played by Arnold Schwarzenegger who had visualized object detection of some objects like some rednecks in some bar, and dogs and etc. Nowadays there are a lot of different interesting use cases involving object detection. You can use it to localize a ship entering a port and classifying its type. Also, object detection is essential for self-driving car software. And I'm talking here about things like pedestrian detection, traffic signs detection, and actually other things that we humans do while driving.
That's actually very interesting. Can you tell us a little bit more about how object detection is tackled by modern machine learning models?
Of course. Since 2013, when Ross Gershik introduced rich features with convolutional neural networks framework, deep learning models have become superior for this task. There are two main ways to tackle the object detection problem. One is to treat it as a classification task only, or the second one is as a regression plus classification. In case of a classification only, detection frameworks consist of modules for generating regions proposals, sometimes called regions of interest, shortly ROIs. Then those regions are classified whether they contain wanted object or not.
So could you tell us how this RCNN works exactly?
In original version, RCNN framework consisted of three major steps. Region proposition by selective search, feature computation by deep neural network. In original paper it was VGG16, and that network should be pre-trained on auxiliary task. And the last step, region classification. So in the first steps, regions are proposed by selective search algorithm that combines strength of exhaustive search and segmentation based on texture similarity. In typical scenario, selective search returns about 2000 regions of interest. Now we need to generate features for those regions. We do it usually by forward pass of VGG16 pre-trained on ImageNet. Those features are used from first fully connected layer, as they are less labels dependent than features from penultimate layer. At last, features are fed to binary support vector machine that classifies regions, responding if they contain object or interest or not. So imagine you're driving a car 50 km per hour. RCNN could detect object once every around 300 meters.
Well, as we can imagine, computing features for 2000 regions and classifying them takes a lot of time, and original RCNN framework was quite slow. Processing single image took about 20 seconds, but we can shorten the time now, right?
Fortunately, yes. Ross Gershik, the same guy from RCNN, have introduced later fast RCNN and even later faster RCNN, cutting down time of processing to fractions of seconds. So faster RCNN is an end-to-end neural network that contains small neural network called region proposal network.
And how does it work?
Instead of computing independently features for those 2000 regions, we compute features for whole image just once, preserving their spatial locations. RPN network shares full image convolutional features with the detection network. The RPN is a fully convolutional neural network that generates regions proposals along with objectness scores. Using the recently popular terminology of neural networks with attention mechanisms, the RPN components tells the unified network where to look.
You also mentioned another way to handle object detection as classification plus regression, right? How it's done in this case?
Yeah, in this scenario we predict a class of object and regress directly coordinates of boxes that bound predicted objects, called bounding boxes. One of well-known regression models is YOLO. It means you only look once. It's like from this movie with James Bond, you only live twice. YOLO was introduced by Joseph Redmond, Ross Gershik, the guy from Faster RCNN. This guy did a lot of job in object detection. Santosh Dival and Ali Fajardi. It is especially useful for adapting to object detection in videos due to its super speed. In tiny version of the network, it's even 160 frames per second. So Faster RCNN, despite its name, it's not fast enough to perform at that pace. So if you remember example with car driving 50 km per hour, YOLO detection's time corresponds to just 30 centimeters of road. Latency that may be acceptable in self-driving cars in contrast to RCNN.
So could you just briefly explain how YOLO works?
Sure. YOLO splits image into grid. Each cell in a grid predicts boxes and confidences. So the confidences are just probability that box contains the object. Each cell of a grid also predicts a class probability condition on object. In test time, YOLO combines the box and class predictions by simple multiplication to return detections.
Yeah, that's more clear now, and I must say it's pretty cool. We can actually use object detection in many cases. As you mentioned, Facebook uses it for face detection. Is it also used in smartphones nowadays as an unlocking feature, scanning face in order to unlock device, etc.?
Yeah, Face ID have been recently introduced in iPhone X, and face detection is the first step in face recognition pipeline. Other cool use cases of object detection are, for example, people counting, where it's used for analyzing store performance or crowd statistics during festivals. It's also a necessary step for content-based search engines. So, as mentioned before, the street-to-shop search engine. For example, if you're building the system that matches clothes from street, from concerts, from shops, from people walking in shops to photos of those clothes in shop product database. Before actual matching, you need to detect specific clothes on street images. Similar thing is a part of Pinterest machine learning technology.
So, what is the state of the art currently in object detection? Is it one of the things you already mentioned?
Frankly, there are a couple of competitive frameworks. Faster RCNN, deconvolutional SSD, and YOLO in V2 version offer similar performance on benchmark datasets. Last year, improving object detection algorithms was based on applying newer architectures to aforementioned frameworks. Particularly interesting was AutoML project. It's a technique that automates the design of machine learning models. The most recent version of Faster RCNN uses an architecture generated by AutoML called NASNet.
Wait, so a machine learning model that learns to design machine learning models. It sounds like you're going to be out of the job soon, and AI will take over the world.
That's the idea.
Yeah, and we'll have Terminators detecting rednecks in bars.
Well, of course we will, yeah. Well, that's it for today. Let's go back to drinking coffee and scheming about AI bringing the world to its knees.
Sounds like a plan. Thank you very much, Matthew.
Thanks.
And thank you to our dear listeners. We hope that you had as good of a time as we did. Till
Bye.
next time. Bye.
Bye.